Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. Hi, everyone. I'm Madan Muswati from the Research and Software Engineering Group, and it's my pleasure to introduce Dan Marino today. He is no stranger. He spent 2 internships with us hacking on compilers, and he's graduating from UCLA. He works with Todd Milstein at UCLA, and he did his undergraduate in UC Berkeley, and then he worked in the industry for 5 years before he decided that he was getting paid too much, and he went back to graduate school. And so at graduate school, he's been working on different aspects of programming languages. And today he's going to be talking about how to give semantics to concurrent programming languages. Dan?
Thanks, Madan. And thanks, everybody, for coming. All right, so parallel programming is hard. And here is just one illustration of why that's the case. You take this simple C++ program that has 2 variables and exactly 2 threads. And the thread T here sets the variable x to be some newly allocated memory, and then sets the init flag to true. And thread U over here tests that init flag, and only if it's set to true, then it goes ahead and dereferences x. And so the question we want to ask ourselves for this parallel program is, can this crash? And in particular, can we get a null dereference, a segmentation fault here at statement D? And if you don't spend a lot of time thinking about the low-level details of concurrent languages or about memory models, then you probably would say this program looks fine. But in fact, it can crash. And so if parallel programming is so hard, as a programmer I might think, forget this concurrency stuff. I'm just going to continue writing my sequential code. I've gotten good at that, so I'll just do that instead. But there's a problem with this, and that comes back to Moore's law, right? So we have this graph showing the transistor count doubling every 2 years or so, and that's continued all the way up to the present day. But the architecture landscape is changing, and these transistors are getting used in a new way. And so, 5 years back or more, we started hitting physical constraints that stopped us from being able to use these transistors to sort of make deeper pipelines and increase clock speeds. And instead, we saw the number of cores on a chip increasing. And so instead of having this sort of familiar model of a CPU talking to some number of levels of cache, and then talking to memory, architecture started changing, and they started looking more like this, where you had many CPUs and maybe many different caches, and eventually they're all sort of can talk to the same shared memory up here at the top. And so this sort of fundamental change down at the architecture level trickles up to the programmer. And so this programmer who's become accustomed to having his programs run faster if he just waits a year for the faster processors to come out, or to be able to add new features without sacrificing performance, or to have his algorithms work on bigger problems simply by waiting, that's not going to work anymore. He's not going to get this sort of free lunch that he's gotten from Moore's law in the past unless he can start thinking about his program in a parallel way and allow it to scale in this way. OK. So if our programmer is going to be forced to think about to code in parallel, then let's see how he might reason about this example program we had. Think, OK, how could these different threads be interleaved? Well, it could be that thread T runs entirely first and then followed by thread U. And in that case, then we'll set x to this newly allocated memory. We'll set init to true. This will see init equal to true and then dereference x. Everything looks OK because x has already been initialized. Oh, but we could have the case where this interleaving, where actually C executes in between A and B. In that situation, well, when C executes, init's still going to be false, its initial value, and so D won't be executed at all. Again, no program crash. Looks OK. And you can apply the same reasoning if you sort of look at this other interleaving. So OK, that was kind of hard, especially for a 4-line program, to have to reason about that. But the program looks OK. But I said that this program could crash. So what's the flaw here? And the thing is, this programmer isn't sort of considering all of the stuff that's going on underneath the covers across this hardware-software stack. And in fact, when the optimizing compiler and hardware get their hands on this program, they choose to do their optimizations, looking only at one thread at a time. And in fact, they might say, hey, statement B doesn't depend on statement A. They access different variables. There's no sort of data dependence or control dependence there. It might be faster to go ahead and reorder those. So if either the compiler or the hardware does that, then we end up with this situation where this interleaving that's suggested here could happen. And indeed, that would cause a null pointer dereference because C would see an int equal to true before X had been initialized. So why do we want to do these reorderings anyway? And it's because there's been a lot of research, and we've come to rely on our compilers to give us code that performs well by performing optimizations such as common subexpression elimination and register promotion and smart instruction scheduling. And all of these different optimizations have the potential to reorder accesses. Similarly, at the hardware, we have out-of-order execution and things like store buffers to try and hide the latency of cache misses, for instance. And these same features also will cause memory accesses to be reordered. And so what that means is that when we were in the sequential world, the programming language had the same strong sequential semantics that you expected. But now that we're coding in this parallel world, we still want these performance optimizations that we've come to rely on. But then we have to have these weak semantics up at the programming language level where we have to reason about our memory accesses potentially being reordered. And so the result of this current approach of allowing all of these optimizations and then putting up with these weak semantics is that we have nasty bugs. We all know that concurrency bugs are difficult to track down because they may only happen intermittently on certain code paths and certain interleavings. And they can have serious consequences. I just have a couple of examples up here of situations where concurrency bugs caused were very expensive and even caused death in the case of this radiation therapy machine. And so as we see, increasing number of parallel programs because our programmers are being forced to code in this parallel style, and we're seeing increasing core counts, you can only extrapolate this and think we're going to see even more of these nasty bugs as we move forward. And I think that we can definitely do better here. And I think we can do better by taking a kind of a holistic approach. And we can allow programmers to develop these fast and safe concurrent programs by exploiting cooperation among these different layers of the hardware and software stack. So I'm going to talk about two main projects today. I'm going to spend most of my time talking about DRFx, which is it gives straightforward programming language level semantics to a concurrent programming language while still allowing efficient implementation by taking advantage of cooperation across this stack. And then I'm also going to talk, that's what I'm going to spend most of my time talking about. I'll also later talk a little bit about light race, which was a tool I built for that uses sampling in order to have a high-performance data race detector. And a data race is a common kind of concurrency bug. OK, so first I'm going to talk about DRFx. First what I need to do is define what a memory model is. So one way to define a memory model is that it defines the order in which memory operations can execute, or the order in which they can become visible to other threads in the system. And so, as you can see from this definition, a memory model is actually essential in order to describe the behavior of a concurrent program. Because if you don't know what memory writes are visible to what reads in different threads, then you can't say how your program is going to behave. So one memory model is sequential consistency. It was introduced by Leslie Lamport way back in 1979. And the idea with sequential consistency is that memory operations appear to occur in some global order that's consistent with the program order, and they appear that way to all threads in the system. So it's basically an interleaving semantics. And this is, in fact, what our programmer, who mistakenly thought that program couldn't crash earlier, he was using this sort of SC memory model. And so that's basically thought of as the most intuitive memory model that we can provide. But it disallows a lot of these optimizations that I mentioned earlier. And so the current state of the art for programming language memory models are these data race-free models, or DRF0 models. And they give this intuitive, sequentially consistent behavior that we want for a certain class of programs, data race-free programs. For other programs, it provides much weaker semantics. So the idea with DRF0 is that programmers are encouraged to use, and in fact often do use, sort of high-level synchronization constructs in order to communicate between threads, like locks and signal at wait. And so the compiler agrees not to sort of do anything crazy with its optimizations with respect to these operations. And the compiler also can communicate that down to the hardware using fences and translates these into atomic operations. And the hardware is restricted from reordering around those operations. And a program is considered data race free if the programmer has included enough of these synchronization operations so that no two conflicting accesses, that is, two accesses to the same memory location where at least one is a write, so that no two conflicting accesses to shared memory can execute concurrently. So if you have enough synchronization, if you have a well-synchronized program, then your program's data race free, and we get this SC behavior that we want under these DRF models. But we get weak or no semantics for racy programs. So the Java memory model is an example of one of these DRF0 models. And it provides a much more complicated semantics for your language or for your program if it contains data races. C++, the new C++ OX memory model is kind of an extreme version of the data race-free models where they give absolutely no semantics to a program that contains data races. So just coming back to our example program here, you actually can make this a data race-free program. For instance, in the new C++ OX, you can do that by specifying that this init flag, you add the atomic keyword there, and that indicates that it's being used for synchronization. And then the compiler and the hardware are prevented from performing these problematic reorderings that we saw earlier. Okay. So what's the problem with DRF0 memory model? Well, basically, it's that it's very difficult to determine whether or not a particular program has a data race. There are, for instance, type systems for race freedom, but they're limited in their applicability because they generally apply to lock-based code, limited styles of synchronization. Or if they support more, and static analyses tend to be conservative, or if they support different, many variants of synchronization, then they don't scale well to large programs. So that's in the static world. In the dynamic world, it's not enough because testing, you're only testing certain paths of a program. You don't get full coverage. And so you may miss some interleavings, you may miss some paths, and so you won't find all the data races in your program. Furthermore, dynamic analyses tend to be very expensive for detecting races, slowing down your program by 8x or much more than that in some cases. And the fact that it's easy to introduce a data race, you can see that this is actually true by I did a quick search of some Bugzilla databases and found bug reports that were unresolved and had race condition in their description. And here for Mozilla we had 122 of them, and MySQL we had 12. So these are real bugs that happen all the time, and so we end up with this really, for these programs, we end up with this weak semantics or no semantics at all for our programs. So sort of a summary of this is that if we have weak or no semantics for racy programs, and it's easy to unintentionally introduce data races, well, that's problematic for debuggability, because our programmers need to assume that they're seeing non-SC behavior for all their programs, because they're not sure whether or not there's a race in there. It's problematic for safety. In their PLDI paper, Bohm and his co-authors showed how reasonable compiler optimizations that are sequentially valid when combined with a program that has a data race can actually cause your code to take a wild branch and jump to start executing arbitrary code. And that's exactly, that's one of the main reasons why in the C++ OX memory model they give no semantics to a racy program, because this kind of thing might happen. Now in Java, they didn't have the luxury of saying we're not going to give any semantics because they have these safety guarantees they need to maintain. And so they have this rather complex description of what program behaviors are allowed in the presence of a data race. But it turns out that it's so complicated that it's really very difficult to tell if a particular compiler optimization is even admitted by the model. And in fact, Savchuk and Aspinall showed that certain compiler optimizations that were explicitly intended to be allowed by the model, in fact, were not. And so it's difficult to reason with these kind of memory models. So our solution to this was the DRFx memory model. And in this memory model, we take the approach that a data race is a programming error. And as such, we should feel free to terminate a program at runtime if a data race is detected. Okay? And by allowing ourselves this freedom, and as I'll show you by using cooperation between the compiler and the hardware, we get a memory model that has good debuggability. We're going to give sequential consistency for all executions. It's a safe programming model because we're going to halt a program before any non-SC behavior is exhibited. And it's easy to determine what compiler optimizations are allowed. Basically, all sequentially valid optimizations are going to be allowed with a few restrictions that I'll describe later. And so with this hardware compiler co-design and the ability to throw this exception, we end up with strong end-to-end guarantees from the source language down to the actual executions of the compiled code with a 9% slowdown on average. So let's take a look at what the memory model guarantees, okay? The first part of the guarantee is if the programmer gives you a data race-free source program, then all executions of that program will be sequentially consistent. However, if there's a race in the program may be terminated with a memory model exception. So with the picture the way it looks so far, it seems like we need some precise runtime data race detection. But that's slow if you try and do that in software, and hardware solutions are very complex. But we actually have an escape hatch here. If your program has data races, we don't have to raise an exception. We can go ahead and allow the program to continue executing as long as we can guarantee that the behavior that we're seeing is sequentially consistent. And so we take advantage of that in order to simplify the runtime detection process. Yeah?
So you say that if the program has some data race, it may be raising an exception, may be raised, or must be raised?
May be raised.
Okay.
Yeah, we have two options. If the original program has a data race and we're running it, if that data race is going to result in SC behavior, in non-SC behavior, then we absolutely must throw a memory model exception. If that data race is somehow exhibited but doesn't cause non-SC behavior, and we can somehow guarantee that we're still going to get sequential consistency, then we don't need to raise it. So let's take a look at how we do this. Here's our example program for earlier without that atomic keyword. So this is a racy program. We've got a race on both x and on the init variable. And here's that problematic interleaving. And this could have been done by the compiler, this reordering of these accesses. So our insight was that the compiler can actually communicate to the hardware regions where it performed optimizations, regions in which it might have reordered accesses in order to optimize. And it can do that using some new kind of instruction called a region fence that tells the hardware where these code regions are. Now, the hardware's responsibility then is just to detect conflicts, read two accesses to the same memory location where at least one is a write, between regions that execute concurrently. So in this problematic interleaving, these regions definitely execute concurrently, and so the hardware needs to raise a memory model exception. If, on the other hand, the execution looked like this, well then, we had this reordering occurred, but it's not actually causing any problems because, it completes entirely before this other region with which it races starts executing. And so we still have a data race that's been exhibited in this program. There's no happens before relation between these regions. There's no synchronization operation forcing them to execute in one order or the other. But nonetheless, we can guarantee SC behavior, and so we don't need to raise an exception. And so this is the simplification. We don't have to do full race detection. We only need to do data race detection on concurrently executing regions that were communicated by the compiler to the hardware. So we rely on this cooperation, and so there's a set of requirements that the compiler and the hardware need to obey in order to get our strong guarantees that we're looking for. For its part, the compiler partitions each thread into regions by using these region fence instructions. And it puts synchronization operations in their own region. And so this stops, in well-synchronized programming, this sort of stops any regions that have conflicting accesses from executing concurrently, and so we won't raise any exceptions at runtime. It also agrees to optimize only within a region. So it's limited in its scope by these regions that it puts in. But the nice thing is that it can perform all of the sequentially valid optimizations that it wants to within that region, except that it can't introduce speculative reads or writes, because that could raise and cause the hardware to raise an exception in an otherwise race-free program. For its part, the hardware needs to treat these fences as memory barriers, essentially not optimizing across fences, but otherwise can do all the reorderings it usually does. And it has to perform this conflict detection. So that set of requirements, we've formally specified them and used them to establish the DRFx guarantees.
I'm sorry, but can you say a little bit more what is a region fence? And I'm sorry if it's known to everybody in the room, but so is it it's enforced basically some synchronization? The region fence.
So the region fence. So the requirements are that synchronization operations definitely have to be in their own region, right? So in that sense, they are related to synchronization. But they don't. But region fences can be added in places other than right where synchronization operations are. And I'm going to show you later why we might want to do that. Okay, why it can be useful to actually put in one of these fences even when there is no synchronization.
But so even with region fences, they can still be data races. Is that correct?
There can be, yes. Yes, the region fences don't do any additional synchronization. They're just delimiting where that synchronization is.
It's more, I should think of it more as an annotation.
Yeah.
Versus something which is really a synchronization operation which is enforced.
It is an annotation, but it also stops the hardware from moving memory accesses across it.
I see. It's a subtle difference there.
So you said the compiler would insert the region fence if it reordered it, if it reordered those two accesses between init and X, right? So the question is, if the compiler didn't reorder it, but the hardware did, how would it know that there should have been a region around it? Because the hardware could equally well do reordering.
Yes, that's correct. And the hardware needs to, so whatever region fences the compiler comes up with, the hardware also will detect conflicting access. First of all, I should specify that everything's in a region, right? There's nothing that's not in a region. So everything's in a region, and the hardware will always detect conflicts between concurrently running regions. And so if it performed that reordering within there, it would still notice that it conflicted with another region that was executing concurrently.
So the hardware would be required to do the same effective thing if it reordered the read and write, to insert a region of its own.
It won't insert the region because the compiler has already inserted regions. So its response. So the compiler has inserted regions. Every line of code in the program is in a region. And the basic idea is that as long as there's no conflicts between concurrently executing regions, then you actually have a region serializable execution. And it doesn't matter whether or not it was the compiler that reordered those things. The only thing is that the hardware is only allowed to do those reorderings within the regions that the compiler inserted.
So if the compiler didn't reorder, it would put one region around each statement, for example, and then the hardware would not be allowed to reorder regions at all.
That's correct.
It's only reorder within a region.
That is correct.
Okay. Now I understand.
Make sense? Okay. So, we formalized these requirements for the compiler and the hardware. And then use those to establish that indeed these, if the compiler and the hardware meet these requirements, then we get this end-to-end guarantees that we want to give the programmer. And that is that a data race-free source-level program implies that there will be no memory model exception raised at runtime for any execution of that program. And furthermore, if an execution goes through without raising a memory model exception, then that execution is sequentially consistent with respect to the source program. Okay? So I claim that this restricted form of race detection was efficient and simple, and it is. And in fact, there's an analogy here with hardware transactional memory. In hardware transactional memory, we have these transactions that are running concurrently, and you have to detect conflicts between them and then roll back and re-execute a transaction if conflicts are detected. And we actually do something very similar here, but it's actually simpler, because some of the difficulty in implementing hardware transactional memory is doing checkpointing and having to roll back transactions. Here we don't have any rollback. We actually are able to terminate the program because we can guarantee there's a data race. Also, another source of difficulty in implementing transactional memory is because the programmer is controlling the boundaries of transactions, they can be arbitrarily large. But the hardware only has bounded resources to work with, so there has to be some sort of fallback mechanism. Here, our compiler is inserting the region fences, and so we can actually bound the size of these regions. And that's exactly what we do. And this is why you might want to put in region fences even where there aren't synchronization operations. And so by bounding the number of memory locations that are accessed in any particular region, we ease the hardware, the job of the hardware. And the disadvantage to this is that we're limiting the compiler to optimize only within regions, so we're sort of further limiting its scope by bounding these regions. But we would like it if the hardware wasn't necessarily required to limit its scope of optimizations. And so we actually distinguish these bounding region fences from the region fences we insert for synchronization, so that the hardware can actually coalesce these regions at runtime if the conservative compiler analysis, if it has resources available, either because it has a lot of resources dedicated to conflict detection, or because the compiler was conservative in its bounding analysis.
Question. So if the hardware, why do you insert it in the compiler? I don't understand, why would you compute those bounds in the compiler and not just do it in the hardware?
Because the compiler has to agree not to reorder accesses across the regions. Otherwise, we can't get the end-to-end. We could get sequential consistency for the compiled program, but not for the original source program.
Okay.
Does this mean that you can't put loops inside regions?
So this is the case for our implementation. That brings me nicely to the next slide. So we took LLVM and we did this naive bounding analysis. And for this analysis, we did put a region fence at every loop back edge. So essentially, you have a single iteration of loop. Now this is naive, and you could do something else. You could unroll the loop and have several iterations be in a region, and then loop that way. So we just haven't implemented these more advanced features to make the analysis, well, not even the analysis, but just make the insertion of region fences better. And so
So those fences that the compiler inserts, for the reason you just mentioned, really are very different in the sense that the compiler is actually telling the hardware, you may put a boundary here because I didn't reorder across it.
yes.
It doesn't mean the hardware has to put it.
That's exactly right. So the hardware is actually still able to do reordering as long as it has resources available to do this conflict detection over the larger region. Yeah. So that's maybe will explain why we don't see such a huge performance loss when we are doing this sort of putting this naive thing of putting a fence at every back edge, is because the hardware is still able to do all the reordering it wants across those loop iterations as long as it has the resources. Okay, so that's what we did for the compiler based on LLVM. For the hardware, we simulated this in FES2, and we used a lazy conflict detection and did this region coalescing that we're talking about when possible. And we measured the performance on these parallel benchmarks, Parsec and Splash2. And Parsec in particular is supposed to capture, the types of programs we'll be running on multi-core machines, the emerging workloads for those kind of machines. So these are the results we saw. On average, 9% slowdown. The blue portion of this bar roughly corresponds to the overhead that was caused by lost optimization opportunities in the compiler. So because the compiler is being restricted to these regions, it's not able to do all of the optimization it normally would, and so that's what the blue portion of the bar represents. The red portion is from the lost hardware optimizations and the additional cost that the hardware has to incur from doing this hardware conflict detection, this sort of race detection. So if we were to improve the way in which we were inserting these bounding fences, I think that there's a lot of hope that we could get this blue section of the bar to shrink further than it is now and actually bring these overheads down. Yeah?
Just your last sentence there. So in other words, you don't think that it's the case that those optimizations would destroy the correctness of the program in these cases?
If there was a data race in that loop, then you might be more likely to raise a memory model exception at runtime because you're doing conflict detection over larger regions. And you may have broken it by doing some of those optimizations, but we're going to catch it.
But you think that these programs may have such bugs?
They may have such bugs. I think we did encounter a race in one or two of these benchmarks that seemed to be an intentional race that was in there, but for the most part, these are race-free programs, and so these, this really is just lost optimization potential. Yeah.
So did your compiler do some unrollings to get over this limit?
It did not.
It did not.
And it hasn't. Yeah, we haven't done that yet. Okay, so for a summary of this DRFx stuff, this idea of having the compiler communicate to the hardware regions where it might have performed optimizations, and then doing a lightweight form of data race detection, along with this freedom to raise an exception and terminate a program on racy execution, gives us a memory model that's easy to understand both for programmers and compiler writers. The programmer is going to get understandable SC behavior for all programs, unless, of course, they're terminated, in which case they know they definitely have a data race in their program. And the compiler is allowed to perform all its favorite sequentially valid optimizations without tricky reasoning like you have to do in the Java memory model, with a few restrictions. And it's efficient, because it admits all of these optimizations, and because the detection that we have to do in hardware is actually fairly simple. And so we saw that we only saw a 9% slowdown on average, so which I think is a reasonable price to pay for an understandable memory model. Yeah.
So just a general question. So from my point of view as a programmer, where I want to just write reliable programs, it's made it. It's great that it will either execute correctly or it will fail, but I still am not guaranteed when I've written a given program and even done fairly exhaustive testing that it might not raise this memory model exception out in the field and still fail in some real world condition and still cause some problems. I'm guaranteed. It's nice that it's going to either go correct or it's going to really, really fail, but I still, if I want to write something that will be reliable, I still have this issue of can I test to find all of the possible data races. Is that correct?
Yes, you do. And I think that still would be a problem that you would want to address. I mean, I think it's still worth looking for data races, even when you have a memory model like this. Perhaps even more so, because you don't want to have these kind of crashes in the field. I mean, there are compromises that you could think of. You could use DRFx for development and then say, if you think that it's better that your program limp along in the field, not do this conflict detection. I don't know if I would recommend that because that would just make that more difficult to debug. But that is, that's an interesting point in this. But I don't know that it's any worse than saying that your program can branch to arbitrary code and start executing either. So, yeah. All right. So if there are no other questions on the DRFx portion so far, Yeah, Sebastian.
One more question. So you talked about the synchronization operations have to be in their own region. What do you include in that group of synchronization operations?
Well, we would include all of your low-level sort of compare and swap interlocked operations. Those would need to be in their own, in addition to library calls to something like lock and unlock, and things like this.
So what about like inside the library call to lock or unlock? You're going to have data races, right? Because these things may read and write locations.
So I think that we can do, so there's two different approaches you could take here. You could say that the libraries are not subject to the DRFx and sort of isolate them and say that you just put those in their own region. You could also choose to actually only put lock and unlock, or sorry, only consider the lowest level machine instructions as being synchronization operations, and then insist that those lock and unlock actually be coded in a way that there were no, quote unquote benign races or races that people, considered the underlying machine's memory model to get correct. That you actually had to have used the atomic operations. In our tests, these programs were using pthreads, and we did not recompile the pthreads library, and we put those calls in regions. Okay, so I'm going to move on to talk about light race, which uses a sampling approach in order to make data race detection lightweight. So we don't have DRFx hardware. DRFx requires hardware support, so what can we do in the meanwhile? Well, one thing we can do is we can try and find data races using software tools. We want to find data races for multiple reasons. First of all, because of these, the exposure to these weak memory model effects that we were talking about all through DRFx, these reorderings and unintuitive behaviors. But even if you had sequentially consistent semantics, data races still can indicate bugs because oftentimes they indicate some violation of a high-level consistency property. For instance, if you don't have mutex locks inserted to protect the state of an object is consistent. So you still want to find data races even if you had SC, and especially when you don't have SC. And as I mentioned earlier, static techniques are rarely used. It's an active area of research, and there's good work in type systems for avoiding races in lock-based code. But for code that doesn't use locks, then you're sort of left out in the cold. And so that's where dynamic race detection has some advantages. It's able to easily support any kind of synchronization down to low-level compare and swaps. And when they report a race, dynamic race detectors are capable of doing that with having no false positives. On the downside, dynamic race detection has low coverage because it's only run on the test cases that you give it, and only on certain interleavings. And so you can miss bugs. And in addition, there's also very high overhead for doing dynamic race detection. Precise detectors, the fastest ones slow down an application by 8x, and some of them out there are 50x or 100x. And so as a result, developers and testers are unlikely to use these tools. And so light race, the goal here was to sort of keep these advantages that dynamic detection has and mitigate some of these disadvantages. And the idea is that if we can make it lightweight enough, then we can increase the coverage by running it all the time, maybe even during beta deployment. And we also want to maintain this feature of dynamic race detection that we're able to support all of the different synchronization primitives. It's also very important that we don't give false positives, because the last thing we want to do is send developers on a wild goose chase looking for a race that doesn't exist. That's not a way to get people to use your tool. And we found that this sampling approach was actually effective here. We were able to run it on x86 binaries. We ran it on Apache and Firefox, on these concurrency runtime for .NET, and the Dryad distributed application framework. And ended up finding 70% of the races that were present that were exhibited in a particular execution by sampling only 2% 2% sampling rate, and that translated into a 28% slowdown versus a 7.5x slowdown for the fastest full data race detector we could build. So here's what the architecture looked like. We take an x86 binary and we instrument it to log events of interest, which in this case are memory accesses and synchronization operations. And then we generate at runtime a log of these events, which we then post-mortem after the execution analyze using happens before race detection to report races. And the idea of using sampling then, of course, is to reduce the number of events that we have to analyze, and that should speed up this part of the code and also the detection process. So sampling has been shown to be effective in other contexts. So in profile-guided optimization, for instance, this has been very effective, and in ASPLOS 04, the SWAT tool was introduced, which found memory leak bugs using sampling very effectively. But it's not clear that you can apply this technique easily in the domain of race detection. And the problem is that most accesses don't participate in a race, and furthermore, by definition, we need to capture two accesses, the two racing accesses, in order to do this. And at the same time, we want to avoid these false positives. And I'll explain why that we have to be careful with that in a moment. So let's take a look at what happens before race detection looks like. So here's a graph of two threads, and program order creates happens before edges within a thread, and then synchronization operations induce happens before edges across threads. And here we have a properly synchronized program that uses locks to make sure that you're not writing X at the same time that you're reading X. And we know that there's no race here because we can actually draw a path between these two accesses in our happens before graph. If we had an unprotected access outside, then we have a data race because we can't draw a path between them. So we can see why why dynamic happens before race detection is very, very expensive. And that's because we have to monitor, we have to do some extra work at every synchronization operation and every memory access. So we want to use sampling to get rid of some of these. And we notice that, if we miss one of these memory accesses, well, we might miss this data race here. For instance, if we didn't log this read of X. But we're already missing bugs. We're in a dynamic analysis. We're only testing some paths. So maybe if this doesn't happen too often, we'll be OK with that. However, if we were to not log one of these lock operations, for instance, well, that can actually affect the happens before graph. And so we can end up reporting a false race between these things that are actually properly synchronized. So the bottom line is we use sampling for the memory accesses, but we do not sample synchronization operations. We log every synchronization operation that happens. So how are we going to do this sampling? We want to find both of these accesses and have a low sampling rate. So the first thing that I tried was, well, why don't I see how random works? And it actually wasn't nearly as bad as I expected it to be. With a 10% random sample rate, we detected around 25% of the races that were exhibited during an execution. And if you bump that up to 25%, we found 45% of the races. But I should point out that this is still, if you're logging a quarter of the memory accesses in your program, you're going to slow down your program a whole lot. So this is not really great. And in fact, we can do a whole lot better. We end up sampling only around 2% of memory accesses and still finding 70% of the races in the program. Yeah?
How do you do the sampling?
So the sampling is based on this cold path hypothesis. Okay? And what we consider code to be cold if it hasn't been executed before in a particular thread. Okay? And that was important, it turns out, that we did this per thread. And sort of the hypothesis was, especially if you have a well-tested program, then the races between hot paths are already going to have been found and fixed. And that we want to focus our effort on these per-thread cold paths.
What's the cost of logging all the synchronization operation?
The cost of logging all of the synchronization operations plus the 2% of the memory accesses ended up being a 28% slowdown on average over our benchmarks, and it varied a bit.
So among this 28%, most of it then is due to the synchronization?
Yeah, I would say that is true. I don't remember this has been a while since I did this, I don't remember if I looked at exactly, I think I did break down exactly what the synchronization cost was versus the memory. but I would say that most of it was due to that. Right, so here are those results that we got. These first two columns were calculated by running a special version of the tool that actually logged all accesses. So that means it's actually performing full data race detection, but noting along the way which of those accesses would have been sampled by our sampler. We then find all of the distinct pairs of racing instructions that were exhibited during that execution and see the percentage of those that were found by the sampled, if we only used the memory accesses that would have been sampled. And so that's how we get this number of an average of 70%, 67% of the races exhibited during a particular execution found by our sampler. And then this is the effective number of memory accesses that were logged in each of those applications. And then, of course, over here, we did the regular tool without doing the full logging to see what its performance would be. And then this full logging slowdown was we took out all of the overhead of sampling and deciding whether we were sampling or not, and just did as fast as we could, using the same infrastructure sort of to log all of the memory accesses and the synchronization operations. So doing that full logging, we slowed down 7.5x as opposed to just 28% slowdown for the light race version.
So how do you know how many races, how do you know all the races?
I know all the races that happen during a particular execution, that are exhibited during a particular execution.
Okay, so you did like a separate tool.
It was a tool that did, yes, it was a tool that logged all memory accesses and all synchronization operations. And so from that, I can do happens before race detection and exhaustively find all of the races that were exhibited during that execution.
Those are bugs, right? Basically.
Well, you have to argue with a developer to tell them that they're bugs. We did have some, we did find something that at least we could get people to admit were performance problems because of these races, like missing us scheduling something because of a race or something like that.
Benchy and Firefox are safe to use, even though there are a bunch of races.
I don't think so. I think that I think that we should aim for having absolutely data race-free programs. I mean, that's why DRFx seems like a reasonable memory model for me. But
it's kind of funny, right? You make this race checker, so you even say how many you find, like of the real races, and then you're basically saying nothing happens, right? Like no one really cares about that they're races.
Yeah. I wish that we could change that perception. I really do think that it's going to get worse as we get more and more concurrency going on. These data races actually may, exhibit real problematic behavior.
So you're saying like just in real executions, you almost never observe the bad behavior, right?
Yeah.
Because the race, just needs to happen, right? And then even get like bad results.
I think the problem is that the developers think at least they have thought the race through and have determined that, even though it's a race, it will not cause any harm. So if they're right or not is a completely different question, but that's why they will fix it.
So if they're right, it means like race detectors are not useful. If they're wrong, right? So I'm kind of wondering like how many races are actually benign, right?
Yeah, and I think that's an excellent question, and it's something that we kind of struggled with in analyzing this because, diving into a code base like this that's large and then trying to determine whether some race report is potentially benign, my initial reaction because of just my attitude towards the data races is you shouldn't be programming with data races, so this isn't a benign race. But, looking at that with like, okay, if I really reason about this, do I think it can exhibit bad behavior? That's difficult to do. And so I would like to know how many of these were quote unquote benign or intentional.
It may change, right? With newer chips or architectures or memory chips,
For sure.
So what would you recommend to a programmer who is, say I'm writing a lock implementation myself and I want to make it really efficient, and I know that if I use interlocks for everything, it's not going to be performing the way it should. I know I need to use regular loads first to test, for example, if it's free. So what should I do to write this lock?
Well, I mean, that's a difficult question. I mean, and that's a practical issue that you have to deal with now. You know, I mean, I would say long term, you want to take away the incentive for doing something like that. You want to say, you know, have your hardware or your compiler be smart enough that it can do, you know, it can make a high performing lock for you with you saying exactly, you know, so using these operations.
The compiler should take over responsibility for all low-level synchronization.
That would be nice, and I don't think that when it comes to systems code that's always going to be feasible. I think you're always going to have someone that needs to get their hands in at the low level and do some of this stuff. And for that, you know, I don't think that this necessarily addresses that. But I mean, ideally, you want to be able to verify that using something. I think you have a tool for you know, verifying that fences, you know, you have the right fences in. So I mean, low-level verification would be great. I think that. Bottom line is, I also think that you need to have the developer explicitly annotating this kind of behavior in a readable way so that tools are able to reason about it and help that. And I think that that's key. Yeah.
So these percent of races found are percents. I'm curious, can you give us an intuition on the raw counts? I mean, were like tens or hundreds or?
For most of these executions, so let me distinguish between, first of all, a particular static, what I'll call a static data race between two lines of code may exhibit itself many times during an execution. And so I think for some of these you're talking about, you know, definitely hundreds if you count repetitions. If you just count the number of static, which is what I'm doing here, because generally the sampling version, you know, only found a couple of one that was exhibited a lot of times in the full logging. Then, you know, I think that when it, you know, for like concert and dryad, I think it was down around 15, you know, that kind of order of magnitude. It's static.
So did you take a look at any of these and see if they were in, for instance, the bug reports or file bug reports?
I did not see if any of them were in the file bug reports for Firefox. For concert, we did track back one of them and go to the developers, and they were convinced that it was benign in a sense, but that, you know, a task that was ready to be scheduled wouldn't be picked up for some delayed amount of time because of the race. But they were willing to live with that.
Did you get an understanding that the willing to live with that was for performance reasons? Was that their kind of push?
I also think that people don't like to fix races because it's not always easy to do. You don't know exactly what synchronization you want to introduce where without causing, you know, being very coarse-grained and causing a lot of performance penalty. Yeah.
Is there any way that you can sort of test your DRFx model on these actual runs and see which ones of these races that you measured in the full logging were actually still sequentially consistent?
That's interesting. To see whether they were happens before races that were very far apart, you mean, so that they wouldn't cause any problem. That would be an interesting way to combine these, yeah.
But you don't have that?
I don't have that information. So quickly, I'm not going to describe all these different samplers that we use, but I just wanted to show this because it's kind of a cool graph. These cold path hypothesis samplers are these two on the left. The bar shows the percentage of data races that they found in executions, and the dot shows the percentage of memory accesses that were sampled. So you want a dot close to the bottom and a tall bar. So these obviously are doing pretty well. Just for fun, I did this uncold path sampler, which logged everything except for the ones that would have been logged by a cold path sampler to see what happened. And obviously, you know, 99% of the memory accesses were logged, and we still only found, you know, a third of the races that exhibited in the program. And I don't have any really deep idea of exactly why this is the case, but it is good empirical evidence that this cold path hypothesis has is reasonable. So just real quickly, you know, yeah.
Does this mean that you at least are going to miss 30% of all the races in your current approach?
No, because of this idea that a static race may exhibit itself multiple times during an execution. Yes, exactly.
Well, but since it's static, why would it, if you have a hot race, then this will not be measured in your system? Or just with lower frequency?
With lower frequency, adaptively backs off. So I'm going to just quickly sort of position this with some of the related work, both DRFx and light race. Obviously, DRFx is a continuation of all the work that's been done in memory models, both at the hardware level and at the programming language level. And what we wanted to do was give as strong a guarantee as we could while still allowing a lot of these optimizations and by using this idea of race detection. And so there's been also a lot of work in hardware and software race detection, but none of those solutions were either high performing enough to use in DRFx, or if they sacrificed precision, they didn't do it in a way that we could sort of harness to still give strong guarantees. So we had to sort of do something different there. Obviously, light race is a software race detection tool, and it was the first one that used sampling in order to make things lightweight. There was work back in the early 90s on detecting SC violations that we were inspired by for the DRFx work, where in the hardware they detected races between in-flight instructions in the processors and then terminated or reported a race or terminated the program if that happened. And so our insight here was, okay, how are we going, that only gives you SC for the compiled binary. How are we going to raise that all the way up to the programming language level to give an end-to-end guarantee? And so the idea of regions was key there in order to allow that to happen. There's also been other work on memory model exceptions. We're not the first to suggest that it would be nice if we could terminate a program when there was a data race. And that's been suggested in the context of full data race detection, and then in work that was concurrent with ours in this conflict exception work by Lucia et al. They do something very similar where they detect concurrent conflicts between regions, but they don't do this bounding that we do, and in fact that allows them to give a slightly stronger guarantee, which is serializability of synchronization-free regions of code. The trade-off for that is that they have to handle this sort of unbounded detection scheme, and it makes the hardware more complex. So I'm running a little long, so I'll try and quickly finish up here, but I'm going to discuss a little bit about some ongoing work and future work. So I wanted to pose the question, is SC actually too slow? This is kind of what DRF0 models and DRFx work. We all sort of are working under this assumption that if you try and do SC, then you can't do all of these optimizations, and your code is going to perform horribly. So, but then you notice that in the hardware community, there's been all this architecture research that shows how you can really reduce the gap between a model like SC and a really weak memory model like release consistency. And it's not just in the research. I mean, in fact, x86 provides a variant of TSO, which in many senses is a very strong memory model. It's not as strong as SC, but it has a straightforward operational semantics that's recently been described. It's easier to understand than, for instance, the Java memory model. And clearly it's giving stronger guarantees than the C++ OX memory model because it doesn't behave arbitrarily in the face of data races. So if the hardware community is able to do this, maybe the compiler is where we're going to lose all our performance. So, what's going to happen if we try and make an SC preserving compiler? And so the idea here was, I'm going to take LLVM, which is a state-of-the-art optimizing C compiler, and then check every transformation, every optimization that it does for its potential to reorder accesses to shared memory. Then disabled passes or modified them to be SC preserving because you only have to disable the pass, for instance, for shared variables. You can still allow reorderings of local variables. So that's what I did when I was modifying these passes. And this included things like loop invariant code motion, global value numbering, which does a form of common subexpression elimination, and many other passes. And so I took this new compiler, which I should distinguish this from other work in SC compilers that actually insert fences to make sure that your program behaves SC on a particular architecture, because that is not what this is doing. This is just not performing any non-SC optimizations itself. And then I measured the slowdown of this compiler, this restricted compiler, when running on stock hardware over fully optimized version of LLVM. And these are the results that I saw over the parsec and splash benchmarks. On average, a 2 or 2.5% slowdown. Now there's, this face sim application, we see a 35% slowdown, which is pretty severe. But for most applications, it looks okay. And in fact, in some cases, the compiler appears to have been stepping on its toes a little bit. We get slightly better performance when we disable some of these optimizations. So is 2.5% too much to pay for an understandable memory model? I would say absolutely not. 35% might be, though. So if you're really interested in writing FaceSim, then maybe that's going to be a problem. So I was thinking, hardware, it manages to close the gap by performing optimizations optimistically under the assumption that there are no data races, and then recovering if there's a potential race encountered at runtime. And it does this by monitoring cache traffic. And so it says, if no one has accessed this cache line since I got it, then everything's okay, my optimization was okay. Otherwise, I squash computation and re-execute. We can actually allow, if we can change the hardware so it actually exposes this mechanism to the compiler, then we can actually do the same kind of thing in the compiler where we optimistically optimize, and then if we notice a race, then we roll back and execute unoptimized code. And that actually allowed us to reduce the overhead on FaceSim by half just by applying this technique to a single optimization pass, the common subexpression elimination or global value numbering pass, actually, in LLVM. So just before concluding here, I want to point to this quote by Sarita Adve and Hans Bohm, who both have a lot of experience working in this area of memory models. Sarita is very instrumental in the Java memory model and Hans in the C++ OX memory model. And in their communications of the ACM article recently, they said, "We believe a more fundamental solution to the problem will emerge with a co-designed approach where future multi-core hardware research evolves in concert with the software models research." And this is exactly what we were doing in DRFx, and I think to very good effect, and I think that we can continue to do that into the future. Now, in the near term, I would like to think about ways of adding additional flexibility to the DRFx memory model. Is there a way that we can support sort of explicit benign races in the program without allowing those to sort of bleed in and violate our safety guarantees that we want to provide? Or is there sort of an analog to the C++ low-level atomics that gives us more information about exactly how synchronizations are being used? In terms of this SC preserving compilation, I think we need to sort of, this is a surprising result, this thing that on average we're only seeing a 2% slowdown by disabling all these optimizations. So we need to keep on doing this on some more benchmarks and sort of see exactly which optimizations are important in what situations. And additionally, I'd like to be able to sort of formally capture exactly what kind of optimizations allow these interference checks, which are the mechanism I was talking about that allows the compiler to do the thing similar to the hardware to optimize optimistically and then roll back if interference was encountered. And then, more long term, I think that this idea, this holistic approach of considering all levels of the programming stack is going to be really important. And I think we need to allow programmers to express the intended concurrent behavior of a program or the intended synchronization discipline, to express that in a machine-readable format at the high level. In some cases, for many applications, hopefully that takes the form of some kind of a declarative description of the parallelism they want to see. But for some low-level system stuff, we may still need to have low-level synchronization disciplines like read, copy, update. But then hopefully we can communicate exactly how we're intending this discipline to work so that our compilers and static analysis tools can take advantage of it. In the case over here of the more high-level parallelism descriptions, then the compiler can take care of generating high-performing, low-level parallel code. And over here, hopefully we can flag discipline violations and bugs that the systems programmer was unaware of. And I also think that there's definitely more opportunity here at the interface between the architecture and the compiler for getting higher performance out of our parallel programs. For instance, maybe having the compiler distinguish local variables from shared variable accesses somehow to the architecture so that it's able to perform more aggressive optimizations on local things just like the compiler can, or somehow communicate memory sharing patterns to get better performance. And in short, and I think that this applies not just to multi-core architectures but to all the future architectures that we're going to see. So together by taking this holistic approach across the stack and hopefully harnessing some cooperation, we can get programmers to develop fast and safe concurrent systems. And that's it.
Yeah.
You report like a 90% overhead of the hardware and the MIS software, the MIS compiler optimizations in the first part for the DRFx. You also said later that that you hoped that no one would write programs with races at all. And indeed, the number of programmers who write programs with races intentionally, must be a very small part of the population.
Yeah.
So my question is it worth it to complicate the hardware and get those slowdowns just so that we can accommodate those few programs written in that way? Or are there better ways to harvest those bugs?
Well, so what I'm worried about are the programmers that are not intending to write programs that way and are actually writing racy programs unintentionally. And that's where I think that this can be very... Now, if your question is, if I had static techniques that allowed me to guarantee race-free programs while still being expressive and high performance, then I would say that is great. But it's proved very difficult to try and achieve that. And so I think that whether it's DRFx or some other technique, I think this idea of leaning on the hardware a little bit to let us do this, more easily is reasonable.
So let's see. So if the programmers don't intend the races, they should have used better programming constructs, probably like locks maybe or something. But if they have races in their programs, and even if they perhaps intended to use locks, then it seems like the light race would be a better attack to find those bugs and change the programs.
Right. Although, I agree. Although the problem with that is that you're still not guaranteeing that you're going to find all the races.
But even if you guaranteed sequential consistency, if the programmer did not realize that there were races in the program to begin with, the program probably isn't correct, right? So
that's true. And but the nice thing there though is at least you can reason in that natural, intuitive way about what you're seeing happen. You can say, okay, this must have happened before this, which happened before this, and then it got interleaved this way, as opposed to thinking this statement could have arbitrarily executed early. That's why I'm seeing this value in this register. So, it really does become a debugging nightmare when you have these weak memory model effects.
Thank you.
All right, thanks.